Hello everyone. Let's take a look at the next problem. Prove that the angle at the center of a circle is twice that at the circumference. So my first thought is this isn't exactly a well-posed problem because it's not talking about how we construct the angle, but I'm definitely assuming that we have an arc on a circle and it's talking about the angle subtended by the arc with respect to the center or with respect to another point on the circumference. So let's draw a little figure about a little diagram of what's going on here. So I've got my circle. In fact, maybe it'll help to draw it a little bit badly so that we don't get, so our intuition doesn't get misled. We'll call the angle of that arc theta, and then it's a fairly well-known theorem that if I have another angle here, alpha, subtended by the arc, but with the other point on the circumference like that, we're asked to show that theta is equal to 2 alpha. How might we go about doing this? So, okay, let me redraw my diagram here a little bit bigger so I have more space to label things. And I'm also going to fix a diameter here and say that one point is, and say, you know, the arc that I have that I'm concerned with and one of the opposite points both lie on the diameter. Now, this means I'm only proving this relation for one particular case of the problem, but then if I can also prove that this angle alpha doesn't depend on where I lie on the circumference, then I'd be finished. So let's say the radius of the circle is r. I'm just sort of going to start labeling some points and writing down some distances of things to see if see if I can figure anything out here. Let me get rid of this. I don't really need that anymore. I've got it on the other side. Okay, so now that now that I've labeled that as r and that as r, here I have the angle is pi minus theta, around there. So I should be able to write down the length of this side. I don't know if that'll matter. This angle here is of course also alpha because it's an isosceles triangle. This angle, well, that's a right angle. I'll just label it like that. And so this angle that I'll call beta, this is going to be pi over 2 minus theta. And I also have that alpha two alpha plus pi minus theta is equal to pi. Oh, look at this. We're already done. 2 alpha equals theta. Okay. So I didn't really need much of this at all. All I really needed is, I didn't need that. Okay. It was nice to, it was a good idea to complete this, just to complete this triangle here. I didn't need to drop that down. So essentially everything we needed to solve this initial part of the problem is here. Now, what happens if the point I'm interested in is not diametrically opposite one point of the arc? Okay, let's try this again. Draw a different figure and see if we can just go through something similar. I don't know how much of this argument will depend on whether this line I'm drawing right now, passes above the center of the circle or below. Okay, so my first instinct here is to connect these. So I'll call this alpha, I'll call this beta. Maybe I shouldn't use alpha and beta again. I'll use different letters. Eta and gamma. Now, what we're trying to prove this time is that 2 times eta plus gamma is equal to theta. Okay, well, by the same arguments we had before, seeing which parts of this triangle, or which parts of the circle and the triangles are a radius and so on. This is gamma also, and this is eta. And so I'm having trouble coming up with more Greek letters in my mind, so we'll call these x and y. I have x plus y plus theta is equal to 2 pi. I also have 2 gamma plus x is equal to pi over 2. Pi. And I have 2 eta plus y is equal to pi. Okay, so I see now if I just sort of subtract some equations from others, I should end up with what I want. Okay, so I'm going to add the bottom 2 equations together. 2 gamma plus eta plus x plus y is equal to 2 pi. And this gives me, well, x plus, if I take the first equation, I can write this theta, theta is equal to 2 pi minus x plus y. And so my last equation here, this bottom equation, just becomes 2 gamma plus eta is equal to theta, right? Just by rearranging things. Yeah, this is kind of nice to do. I've of course seen this this relation between the angle subtended by an arc at the center or at another point in the circumference. I've seen that many times. I don't think I've ever tried to go ahead and prove it myself. My first instinct is that I thought there was going to be some trigonometry involved. I don't know why my first instinct went that way when the relation itself doesn't really have any trigonometry in it. But I just started drawing things and filling in line segments and labeling things and writing down relations between the things I was labeling, and it kind of just pops out. That's a nice problem. Thanks for watching.